some chemical reactions give off gases as their products, or they may use gases as reactants. Gases are difficult to measure by weighing them. It can be done, but it's tricky. So we often specify the amount of a reactant or product that's a gas by giving its volume, its pressure, and its temperature, because from that information we can find the number of moles of the gas. So the ideal gas law, PV equals nRT. We can use that to find the number of moles by rearranging the equation. So the moles of gas is equal to the pressure times the volume divided by RT. You have to have the pressure, volume, and temperature in the correct units, and you have to do your math correctly. But that can allow you to get the moles of gas. And then you use stoichiometry, the mole ratio, to continue on and get the mole to mole. And then perhaps what you're looking for is in grams, and so you use a molar mass. So this is a variation. Actually, let's go back here. This is a variation of grams to moles to grams. The mole-to-mole part is always in there. But if you're starting with a gas, you're not going to start with grams of gas. You're going to start with pressure, volume, and temperature, and you're going to have to use this equation to get to moles. Or that might come at the end. Okay, so we're just changing one end or the other, using the ideal gas law instead of a molar mass. Oops. So let's do an example of this. In this reaction, 4.58 liters of oxygen were formed at 745 millimeters mercury and 308 K. How many grams of silver 1 oxide decomposed? Silver oxide. Well, it's stoichiometry. We've got an equation, we've got amounts, and we're asked about an amount. So let's just write down the numbers under the thing that they're about. So 4.58 liters of oxygen. So I'm going to write that below oxygen, 4.58 liters. And it says at 745 millimeters of mercury, that's relating to the oxygen, and 308 Kelvin, also relating to the oxygen. And then the question is, how many grams of Ag2O? Question mark, grams. So normally we would do grams to moles to grams. We would start with a mass of oxygen and figure out how many moles of oxygen, how many moles of Ag2O, and then how many grams of Ag2O. But they don't give us a mass of oxygen. It's a gas. They're giving us volume, pressure, and temperature. So this is different. We've got P, V, and T, and we're going to go to moles. And we're going to do that using the ideal gas law. And then once we get to moles of oxygen, then we can continue on with stoichiometry. So the number of moles is equal to PV over RT. Is the pressure in appropriate units? No, we need it to be in atmospheres. So we're going to apply our conversion factor, 1 atmosphere per 760 millimeters of mercury. Uh, 0.98026 atmospheres. Zero 0.98026 atmospheres. The volume, they were kind and gave us the volume in liters. And then we've got the ideal gas constant. and the temperature. And they gave it to us in Kelvin, so we don't have to convert that at all. Look how the units cancel out. Kelvin cancel Kelvin, atmospheres cancel atmospheres, Kelvin cancels Kelvin. Liters cancel liters, and we get left with moles. So when we do this calculation, 0.98026 times 4.58 divided by open parentheses 0.0821 times 308 close parentheses equals 0.1775 moles. I'm keeping track of my sig figs as I go along. I've got a whole bunch of numbers with 3 significant figures, and so this is going to end up with 3, but I don't want to round it off yet. That's moles of oxygen. I'm going to take this amount of moles of oxygen, and now I'm going to continue on the stoichiometry path. 0.17755 moles of oxygen. I want to convert that to moles of what? Ag2O. And then I want to go to grams of Ag2O. Then I'm going to put moles of O2 down here, so the moles of O2 cancel out. And I'm going to put moles of Ag2O down there, and so those are going to cancel out. This is a mole ratio. I look at the balanced chemical equation. 2 moles of Ag2O would produce 1 mole of oxygen. So 2 moles of Ag2O for 1 mole of oxygen. And then this last one, that's a molar mass. And silver, 107.9. So we've got 2 times 107.9 plus 16. $231.8 grams per mole for the Ag2O. 231.8 grams per 1 mole. 0.17755 times 2 times 231.8 equals. This is my final answer. I'm going to round it to 3 sig figs. I'm going to come up with 82.3. Anybody else get that? Anybody? Yes, thank you. Any questions? Yes. Would we do the same thing if we were using volume? Like if you're trying to calculate the volume of gas? Yes, it would be very similar. If you were told to find the volume of oxygen that was produced, and they gave you a mass of Ag2O, similar process. You'd go grams to moles of oxygen, and then you would use the information given to go from moles to liters using the ideal gas law. Any other questions? So we can use the ideal gas law to calculate moles of gas, but it gets a little tedious after a while with all the different pressures and temperatures and stuff. And so scientists have adopted something they call standard temperature and pressure. It's abbreviated STP, and you need to know what this is. STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius. That's the freezing point of water. That's a temperature that's very easy to attain. If you want your gas at 0, you just put the container into a big bath of ice water. You wait a couple of minutes, bang, it's at 0. You don't need anything fancy. That's the same as 273 Kelvin. And then standard pressure is 1 atmosphere, also easy to obtain. Okay. Let's calculate the volume of 1 mole of gas at STP. So N equals PV over RT. Excuse me.
That's why it came like
N equals PV over RT. What is the pressure? Oh, stop me when I do this. I'm not calculating moles. What am I trying to calculate? Volume. It says calculate the volume. Psst. PV equals nRT. So I need to divide by pressure on both sides. So the pressure goes away. Volume is equal to nRT over P. That's better. What's N? 1 mole. What's R? 0.0821 liter atmospheres per mole Kelvin. What is the temperature at STP? 273 Kelvin. And then the pressure is 1 atmosphere. So 1 times 0.0821 times 273 divided by 1 equals 22.4 liters. That's the molar volume of a gas. It doesn't matter what the gas is. Any gas. If you have 1 mole of gas particles at 273 Kelvin and 1 atmosphere, it will occupy 22.4 liters. Because the size of the particles really doesn't matter. There's so much space in between, it doesn't matter. This is a very useful conversion factor. It's called the molar volume of a gas. It's the volume of 1 mole of gas at STP. 22 liters, by the way, would be about this wide and about this tall cube. So it's like, that's like a reasonable size, like a medium-sized moving box, right? That's about 22.4 liters. So 1 mole of any gas. 1 mole of helium at STP, 22.4 liters. 1 mole of xenon gas at STP, 22.4 liters. Would they weigh the same? No. Because 1 mole of helium gas weighs 4 grams. 1 mole of xenon gas weighs 131.3 grams. The size, the radius, the volume of the particles doesn't matter, but their masses are different. A helium balloon will float because it's less dense than air. A xenon balloon will not float. It's much more dense than the air because each of the individual particles weighs more. So molar volume makes our stoichiometry calculations with gases much easier. So how many liters of oxygen at STP are required to form 10.5 grams of water? So there's our balanced chemical equation. And we've got 10.5 grams of water, and they're asking for liters of oxygen. So question mark, liters. So normally we would go grams of hydrogen, grams of water. I was trying to figure out how I could convert that into, it doesn't work. It would have to be dihydrogen. Grams of water to moles of water, to moles of oxygen. And normally we would go to grams of oxygen, but here they're asking us for the volume in liters. So liters of oxygen. We could do this using the ideal gas law. They didn't tell us the temperature and pressure, or did they? They did. STP. You could use the ideal gas law, but it's simpler to use the molar volume of a gas, 22.4 liters per mole. That is only true at STP. So 10.5 grams of water. I'm going to go to moles of water, to moles of oxygen, to liters of oxygen. I stick my units in there. These are the sorts of calculations you have to do on that worksheet. It's dimensional analysis come back to haunt you again. All the units canceling out like we need them to. This is the conversion factor for this last one, liters of gas to moles of gas at STP. It doesn't matter if it's oxygen or neon or krypton, or it just doesn't matter. It's always 22.4 liters per mole. So 22.4 liters per mole. What's this mole ratio? It's 1 to 2. 1 mole of oxygen to 2 moles of water. The coefficients here, this has a coefficient of 1, this has a coefficient of 2. And then we need the molar mass of water, and that's 18.02, 2 times the mass of hydrogen plus the mass of oxygen. 10.5 divided by 18.02 times 1 divided by 2 times 22.4. Looking at significant figures, I should have 3 here. 6.53 liters of oxygen would be formed. I'm sorry, you would need liters of that many liters of oxygen to form the water. This 22.4, that is not an exact conversion. The number of sig figs there depend on the number of significant figures that you have in your ideal gas constant. Any questions?